So hello students, welcome back to the channel Z SRA Maths and Tech. Welcome back to our classroom. So we'll continue with the chapter 1 real numbers, and this is going to be our last exercise 1.4. So here we are going to see the rational numbers and their decimal expansions. What is the key point over here? That we have to keep this thing in mind, that x is equal to p by q. So x is equal to p by q. That is an important any rational number that can be expressed in the form of p by q, where p and q are coprimes. Then it will be expressed in the form of decimal, being a rational number. So this exercise 1.4 of real numbers chapter 1 is based on mainly three theorems. The three theorems are theorem 1.5, which says let x be a rational number whose decimal expansion terminates. X be any rational number whose decimal expansion terminates. Then x can be, what are the conditions? Then x can be expressed in the form of p by q. X can be expressed in the form of p by q, where p and q are coprime. The p and q, these two are coprime, and the prime factorization of q is of the form 2 to the power n into 5 to the power m. Okay, where n m are non-negative integers. These are non-negative integers. That means they must be greater than equal to 0. Non-negative, that is the condition. So that is theorem 1.5. For any rational number x whose decimal expansion terminates, that should be expressed in the form of p by q, where q, the denominator q, can be expressed in the form of 2 to the power n into 5 to the power m, and where n and m are non-negative integers. Now theorem 1.6. Theorem 1.6 says that let x is equal to p by q, a rational number. X is equal to p by q, a rational number, such that prime factorization of q is of the form 2 to the power n into 5 to the power m. Again the same condition, where n m are non-negative integers. Again same condition. Then x has a decimal expansion which terminates. X has a decimal expansion which terminates. Again, when the rational number expressed in the form of p by q, where q, the denominator, is equivalent to 2 to the power n into 5 to the power m, then the rational number terminates. This is stated by theorem 1.6. Now theorem 1.7. What does theorem 1.7 says? It says that let x is equal to p by q be a rational number such that prime factorization of q is of the form 2 to the power n into 5 to the power m, where n m are non-negative integers. Then x has a decimal expansion which is non-terminating, repeating. That means, it means till now q was expressed in the form of 2 to the power n into 5 to the power m, but there has to be some other prime integers. So let's focus over here. What does theorem 1.7 says? That for terminating decimals 1.5 and 1.6, 1.5 theorem and 1.6 theorem, and for non-terminating repeating decimals there is theorem 1.7. So the fraction must be first in its lowest form, that is q is equal to p by q. This is the summary of theorem 1.5 and 1.6 and 1.7 as well, on which this exercise 1.4 is based upon. So for terminating decimals, prime factorization of q is strictly of the form 2 to the power n into 5 to the power m, where n m are non-negative integers. That's the condition. Denominator contains only 2s, only 5s, or mix of both. That means either multiple of 2 or multiple of 5 or both. Nothing other than these conditions for terminating decimals as per theorem 1.5 and 1.6. Now coming to theorem 1.7, for non-terminating repeating decimals, again the fraction must be in its lowest form. P and q are coprime. The rational number or should be expressed in the form of p by q. So the prime factorization of q is not of the form 2 to the power m into 5 to the power m. That is not in the form of 2 to the power n and 5 to the power m. That means the denominator has intruder. Intruder means any other prime factor, or say any other prime number apart from 2 to the power n or 5 to the power m, or both. There has to be some other number like 3, 7, 11, any other prime number apart from 2 and 5. Then the rational number expressed as x is equal to p by q will be non-terminating repeating decimals. Okay, I hope this concept must be clear. These are the two basic concepts expressed strictly in theorem 1.5, 1.6 and 1.7. So let's proceed and let's start with the questions and problem solutions. So the first question says that without actually performing the long division, state whether the following rational numbers will have a terminating decimal expansion or a non-terminating repeating decimal expansion. So identifying terminating decimals. So without long division, here we have segregated those fractions which are terminating decimals and non-terminating repeating decimals. So let's start with one of one. 13 by 3125. 3125 here 3125 can be expressed in the form of 5 into 5 into 5 into 5 into 5. That means 5 to the power 5. 5 5s are 25 into 5 125 into 5 625 into 5 3125. So the whole expression becomes 5 to the power 5. 3125 can be expressed. So here denominator has only 5. That means this is terminating. In the second question, 17 by 8, that means 2 to the power cube is the denominator has only 2, so this is again terminating. I hope these are very easy and simple steps. The only thing is that you have to understand the theorem and the basic concept properly. So coming to the fourth of question number 1, 15 by 1600. 15 by 1600, that means we'll have to first 5 3s are 15 and 5 3s are 15, 1 10, 5 2s are 10, 20. So the fraction is reduced to 3 by 320. This can be again expressed in the form of 3 upon 320 can be expressed as 5 into 2, that becomes 10. Again now 32 can be expressed in the form of 2 to the power 5. So this expression becomes 5 into 2 to the power 6. 5 into 2 is equal to 10. That 0 represents 5 into 2, 10. 32 can be expressed in the form of 2 to the power 5. So we can simply straightforward write the expression as 5 into 2 to the power 6. Now since the denominator has only 2 and 5, so again this is terminating. Question number 6 of 1. So 23 upon 2 to the power cube into 5 square, it is already factored as 2 and 5 in the form of 2 to the power n into 2 to the power into 5 to the power m. So it has only 2 and 5 in the denominator, so again this is also terminating. Coming to the next question, crucial step, always simplify first. Look at 8th and 9th question. We will solve these questions. 6 upon 15. 6 upon 15, simply we can write that it should be in the lowest form. Remember, it was stated in the theorem that it has to be in the lowest form expressed as p by q. So 6 by 15 can be expressed 3 2s are 6 and 3 5s are 15. So it can be written in the form of 2 by 5. Again denominator is just 5, so it is terminating. So next question, 35 by 50. Again 35 by 50, it can be divisible by both the numerator and denominator has a common factor 5, so it can be divided by 5. 5 7s are 35 and 5 10s are 57 by 10. Again this is 7 by 2 into 5. So denominator has 2 and 5, it is again terminating. The 6 of the question number 1, 6 problem, 6 fractions given are terminating. Now coming to those 4 fractions which are non-terminating but and repeating decimals. So 64 upon 455. 455 can be factored as 5 into 7 into 3. So 5 into 7 into 13. So 7 and 13s are intruders. That means they are other than 2 and 5. So definitely it's a non-terminating repeating. Again 29 by 343. 343 again is 7 to the power 3, that is 7 cubes. So our intruder 7 is found, so it is non-terminating repeating. Always remember the basic concept, the theorem we discussed in the beginning of this class. So coming to the question number 7 of question 7th part of question number 1. 129 divided by 2 to the 2 square into 5 to the power 7 into 7 to the power 5. So question number 7, it's already given in the form of 2, denominator is given in the form of 2 square into 5 to the power 7 into 7 to the power 5. So denominator has 7 other than 5 and 2 and 5. Denominator has 7 also, though it is a intruder. So this again will be non-terminating. So next, the last the 10th part of question number 1, 77 by 210. So 7 is common, 11 7s are 77 and 7 11 are 70, 7 into 11 is 77, 7 into 30 is equal to 210. So the fraction can be expressed as 11 into 30 or 11 upon 2 into 3 into 5. Again 3 is an intruder over here, so it is a non-terminating repeating a rational number. Let's proceed to question number 2. So question number 2 says that write down the decimal expansion of those rational numbers in question 1 above which have terminating decimal expansions. So we had identified the terminating decimal expansion as 4 terminating decimal expansions, sorry 6, 1, 2, 4, 6, 8 and 9. The trick in action. What is the trick? We have to write the decimal expansion of those rational numbers in question 1 above which have terminating decimal expansions. Terminating decimal expansion. The first part of question number 1 was 13 by 5 to the power 13 by, it was 13 by 3125, which can be expressed in the form of 13 by 5 square. What we will do here, factor denominator. First we'll have to follow these steps for decimal expansion of terminating rational numbers given in the form of fraction. So first factor the denominator, then match powers of 2 and 5 and then convert to 2 to the, 10 to the power n, and then we can easily place the decimal according to the power of 10 in the denominator. So here 13 by 3125 is converted into 13 upon 5 to the power of 5, again multiplying, since 5 has a power 5, we'll have to convert it into to the 10 to the power n. So we will multiply with 2 to the power 5 both numerator and denominator. In the denominator we will get 10 to the power 5, but in numerator here we will get 13 into 32, that is 416. Here 10 to the power 5, so we can easily count the decimal 1 2 3 4 5. So 0.00416 is our answer. Again the second part of question number 1 was 17 upon 8. It was 17 upon 8, which can be expressed in the form of 17 by 2 cube. Again, since 2 has power 3, then 5 should also have power 3. We will multiply the whole fraction with both the denominator and numerator by 5 cube. So here we will get 17 into 125, and in the denominator we will get 10 cube. 2125 upon 10 cube, it can be easily converted into 2.125. That is our answer. Again question number 4. Sorry, again part 4 of question number 1, which is given as 15 by 1600, which can be expressed in the form of 3 upon 2 to the power 6 into 5. So here we can write 3 upon 320. This 320 can be expressed in the form of 2 to the power 6 into 5. So here we have 5 to the power 1, but we need 5 to the power 6 total, because 2 has power of 6. So we will multiply both numerator and denominator with 5 to the power 5. We will get 3 into 3125 upon 10 to the power 6. 10 has 6 powers. The whole numerator comes out to be 9375. The multiplication results into 9375. So 10 to the power 6, as per the denominator we have 10 to the power 6. So we will count 1 2 3 4 5 and 6. So from right hand side we will count 6 places and we will place the decimal accordingly, and this is our answer. Now the sixth part of question number 1, that is 23 upon 2 cube into 5 square. It is already given. So we have 5 to the power 2 and 2 to the power 1. So we lack 5 to the power, will have to multiply numerator and denominator by 5 to the power 1. Okay, so we'll get 23 into 5, 115, and here we'll get 10 to the power cube. Accordingly we'll place the decimal. 0.115 is our answer. Another, there are 2 more questions. Problem number 8 of part 8 of question number 1, which was expressed in the form of 6 to the power 15, that was 2 to the power 5, that can be converted. So now we'll multiply 2 to the power 1 upon 2 to the power 1, both numerator and denominator. Here becomes 4 by 10, that is 0.4 is our answer. Now the last part is the 9th part of question number 1, which is the terminating fraction. So converting this into decimal, 35 by 50, that means multiplying, converting it into the lowest form, 7 by 10, that is 0.7 is our answer. Okay, hope this must be clear to you, all of you. Now coming to the last question, question number 3. Question number 3 says the following real numbers have decimal expansions as given below, that is 43.123456789, 0.120, 1200, 12000, 120, 4 times 0, and so on. This is the part 1 of question number 3. This is part 2 of question number 3, and this is part 3 of question number 3. So here the third part says 43.123, no, this is not 4, this is wrong. 1 2 3 4 5 6 7 8 9. So let's start solving. Before approaching the question, we have to keep one particular thing, important concept in mind, that a real number is rational if its decimal expansion is either terminating or non-terminating repeating. Okay, a non-terminating non-repeating decimal is irrational. So the condition for rational is that it has to be terminating or terminating a repeating decimal. For irrational, it should be non-terminating, non-repeating. So let's start the question first. First part of question 3. So question 3, in question 3 we can see that 1 2 3 4 5 6 7 8 9, that is this is the value after decimal 43.1 2 3 4 5 6 7 8. That means this is terminating decimal, so it has to be a rational number. So prime factors of q can only be 2 or 5. It can be expressed in the form of p by q. Okay, it is a rational number. Now the third part is 43.123456789. It is non-terminating but repeating, so this is also a rational number. But the second part is after decimal it is 120, then 1200, 12000, and 124 times 0, and so on. So this is non-terminating and non-repeating, so it has to be irrational. This is the condition, and hence we have completed our exercise 1.4. So we'll end this video over here, and in the very next video we will come up with the summary of the chapter and brief points, so that we can do the revision and we can memorize all the concepts learned in this chapter and all the problems solved in this chapter based on those concepts. We'll do a quick revision and brief summary of the chapter in the very next class. So thank you very much. Please join us in the next class.